So it's my pleasure to introduce Dr. Subramaniam Ramamurthy, who is a reader in the School of Informatics, University of Edinburgh, and he's also on an executive committee for Edinburgh Centre of Robotics. So he did his PhD at UT Austin, and since then he has been faculty at Edinburgh. He's also a Turing Fellow at Alan Turing Institute, and also member of Young Academy of Scotland at the Royal Society of Edinburgh. And if all this is not enough, he's also vice president of prediction and planning at 5AI. So Dr. Ramamurthy has done an immense amount of work, and his research focuses specifically on robot learning and decision-making under uncertainty, and with particular emphasis on achieving safe and robust autonomy. So looking forward to your talk today, Dr. Ramamurthy.
Thank you, Ashish. So it's a pleasure to be here. It's good to see some familiar faces and many new faces. So to follow up on the introduction a little bit, so I'm a robot learning person, and with a little bit more robotics, and by that I mean that in the way that we formulate questions, we really are interested in solving complete robotic applications. So it's not just that we are using robots, but we are actually interested in taking them out into the field. I'll touch upon this a little bit towards the end as well, but I thought I'll begin then from that perspective and tell you about where our questions are coming from. And then much of my talk will be on the machine learning methods that go into making these robots autonomous and safe. The other thing I might say is that I probably have a few more slides than I really want. So I'm quite happy to have discussions along the way, because the things at the very end are skippable. So to start with, I thought I'll give you a little bit of a perspective on how I think about autonomy. So the idea of having a robot that makes decisions for itself, it goes back to the beginning of AI. So we've always thought about the idea that a robot, at least as AI researchers think about it, should have a lot of autonomy in it. But then when the rubber hits the road and when you take the robot to the real world, then the situation looks slightly different, and then the questions look slightly different. So I spend a little bit of time thinking about autonomous vehicles, and in that space there's a very clean classification that people have come up with. But since then, people have adapted it to other applications as well. And I thought I'll actually apply that classification to this other application of surgical robots to give you a flavor for exactly what people think about autonomy. So if you think about there being a categorization, on the one end of the spectrum, you have what we would call assistance, quote unquote, which means that it's just really a basic remote control robot system. So if you're thinking about this being used in an operating theater, we're saying that the tools have a little bit of controllers inside so that if you shake your hand, then the tool doesn't shake. Right? It's not very sophisticated in the sense that the tool will not do anything that you don't explicitly command it to do, and if you make a mistake, it will make a mistake. Right? That's one end of the spectrum. The other end of the spectrum, which is science fiction, is that there are no surgeons anymore. As a lot of people advocate on Twitter, all of these people have not been trained, they've gone away, they've disappeared, and robots have taken over the world. For a variety of reasons, especially in this domain, you might agree with me that that's maybe not quite desirable, at least not yet. And there's no appetite for it socially at all. Also, when I sit down and speak to my collaborators who are neurosurgeons and so on, I don't see any evidence that in my lifetime we're going to hit level 5. So really, we are in those question mark territory. That's where we are operating, and sort of the boundary of where we are is the kind of thing you might see if you search under robot surgery in Google, which would be devices like Intuitive Surgical's Da Vinci robot. And what these robots do is they take over quite a bit of low-level sensory motor control, and then they leave the decision-making to the user. So the question is, can you push the boundary from just dealing with the low-level control a little bit towards the decision-making side? And then what might you want to do? There are a lot of social reasons why we want to do this. So in the UK context, which is where I'm situated, there's actually a serious skills shortage. So unlike worrying about taking people's jobs, we actually have the opposite problem in that surgeries are actually being postponed because we can't find enough of a team. So it would be perfectly fine to build such a system. Now, from a technical point of view, as a roboticist, when we start thinking about what actually we might want to do. So here's a very basic example of the kind of assistance you might want a robot to do. This is not surgery. This is actually assembly in more of a manufacturing context. But this is in my lab, and that's my PhD student, Svetlin. And what's going on here is that you have this Baxter robot that's trying to help Svetlin as he's assembling another robot. His sequence of movements, it's a plan. So he's going through, pick up this part, put it on top of this. Once I have it, get something else, assemble it, and so on. So it's something that you could specify at a high level, but there's a lot of low-level complexity to be dealt with. What the robot is doing is, from vision and eye tracking, it's estimating what his planned state is. And then depending on what that current planned state is in the execution cycle, and this has branches and so on, based on that estimation, it's taking what would be an appropriate action. And this business of what is appropriate has been told to it ahead of time. And that violet dot that you see there is us fusing vision and eye tracking and putting it in 3D so that we can kind of visualize what's going on. So that's a kind of basic example. And in my lab currently, we are setting up a more serious setup which would mimic an operating theater. And we are trying to look at, whether we can automate things that are done by a typical nurse and a junior surgeon, working our way up. Okay. The point of picking an example like this is to kind of motivate questions, not just in terms of wouldn't it be nice if, but asking, what would these people really want, and can we actually deliver that, right? Now, looking at it from another point of view of the actual tasks involved, there are grasping tasks, manipulation tasks, and so on. I think many of you are probably aware by now that there's a lot of excitement in the robotics community about the use of deep neural network methods. So here are videos taken from various groups around the world doing really exciting things with robots. And so people are really able to do interesting things, particularly when it comes to specialized tasks like grasping arbitrary objects and kind of figuring out what the physical properties of objects are, and so on and so forth. And in the kind of more extreme version of this, when you think about it, what people are excited by is the fact that there is the possibility of having a completely general purpose mechanism which doesn't need any domain-specific knowledge at all, and then it just continually improves. And that's what one is trying to do with a typical kind of reinforcement learning setup. But then if you look a little bit kind of beyond the label, you find that actually it's not so straightforward. I mean, as somebody who runs a robot lab, here again, this is back to my lab. This is one of my robots. And this is a task that we picked as what we would consider to be the most basic task that would interest a surgeon. It's only after we did this that we got meetings with the surgeon I work with. So the task here is to scoop out a little slice of grapefruit. We kind of took away the job of the second hand, so the grapefruit itself is kind of pinned down to the board. But you still have to make some very careful judgments about how you want to move the knife and exactly what the force profile should be so that you can achieve this task. It's not as trivial as it looks. So we do it effortlessly, but we only do it as adults. And it's actually, although it's just cutting fruit up, it's actually quite interesting because for the surgeons, they consider this to be kind of step zero of what is actually tumor removal. If you flip the hard with the soft, this is how a tumor looks in your brain. And so when I look at a problem like this, there are three things that you should note. The first is the fact that the modalities that you need to complete this task are quite diverse. In fact, except for the very first point at which you insert the knife, vision is largely useless in the sense that once the knife is gone in, you don't know exactly what's going on underneath. So a lot of it is in the haptic channels. But then for the haptic channel, you don't have an exact model because it's just a fruit. You don't know what the internal irregularities are, and you're trying to somehow find what that space is. And we don't have that much data in a domain like this because we have to find the fruits, we have to find the demonstrator, we have to find everything. And so we're not talking about billions of examples here, we're talking hundreds of examples. And that's pretty typical of most domains we work in. And so we have to think very carefully about how we want to set up our models, how we want to adapt our methods, what we want to pre-train, what we want to borrow. which means that we can't just go in quite so naively with the use of the methods. We have to think a little bit about our methods. Now, in the robotics community, once you kind of lay out all of these problems, the approach that quite a few of us pursue actively is called learning from demonstration. So in the same way that supervised learning and certain forms of unsupervised learning are kind of the dominant ways of describing a vision problem, in robotics, probably one of the most exciting approaches for robot learning is to say that it is realistic for us to ask a human expert to give us examples of how a task is performed. In that case, it's realistic for us to say, here are a collection of fruits, please cut them up for me. And we can get a normal person to do that much. And then having done that, what we want to do is to pick up everything about what was the task, what variables were important, what specification describes this task, and how do you want to actually perform that, right? So that's what we want to pick up from all of this. But then this question of what exactly is the task is not trivial. So here's maybe a typical snapshot from just day-to-day life. This lady is cleaning the table. And if I just showed you maybe like a sequence of images like this in a video and I asked you what's the task, then you would say, okay, what she's doing is to move this sponge so that the dust comes off the table. But then I ask you, are there specifications that you didn't pick up? And you'd say, yeah, you have to apply a certain amount of force, otherwise the cleaning isn't going to happen. You have to control your velocity so that the dust doesn't spray all out. You have to make sure that you hit these regions. These are all hidden away specifications that are in the data, but then you can't just have it for free. You have to think a little bit about how you're going to get this, right? And then extreme examples of this might be like this. I don't know if, do I have audio?
Yes, I think so.
Okay. So if I have audio, let's see.
Fluffy pancakes, add flour, milk.
In any case, I won't dwell on it. So for the people who are here, you can kind of hear it. But the point is, here's an example taken from one of my favorite movies, which tells you that I'm a little bit older. What's going on here is that the robot has been given text instructions. Not only has it been kind of instructed a little bit, it's been given a recipe. And what the robot's trying to do is to just follow the recipe. It's been told, do this, do this, do this. It's doing it. And at each point, what makes this funny is that it has left out something about the specification, right? Things we take for given, common sense. And so the real question is, how are we going to get at all this and what do we want to do with it? By way of introduction, the way in which all of this is coming together for me is that I'm currently working on a project in collaboration with people in the medical community, where we are looking at this cycle of how do you go from expert demonstration to kind of picking up what might be useful specifications from this, finding ways in which you want to encode that representation and then reason about that representation, and then finding ways in which you can synthesize controllers that then respect these kinds of specifications. So the plan for my talk today is I'll show results from a few different projects that kind of go through this chain. And the kind of challenge in a couple of years is to bring it all together so that I can show you one slick video that does the whole thing. Today I'll show you bits and pieces that kind of cover this landscape. So the big question, of course, and this is, every time I go to a robotics conference, so the last time I was at RSS or last time I was at Coral, there's always a debate about what are good representations. Do we need representations? Should we be using models? And this seems to be like the perennial thing that we all keep talking about. And a lot of what I talk about will pertain to this. And I have a very particular view of this, which is that if we want to get robustness in the sense that I'm hinting at with my introduction, then you really should use some kind of useful representations that encapsulate common sense. It's not, because we are driven by the application, it's kind of not negotiable that you have to structure your models in a certain way. But we go further than that, and our point of view is that there's plenty that we've learned as engineers from physical models, from control theory, and from various principled approaches to reasoning about systems that actually can be brought to bear on this if you can find clever ways of combining that with more modern neural network-based methods. And that's kind of what we are setting out to do. So to start with, sort of as a preamble, I'll show you kind of glimpses of results from an earlier project that kind of get to this question of what do you want from models? What do we mean by models? Because the word is so overloaded that it means literally different things to different people. If I spoke to a statistician, all they mean is a description of a distribution, right? Gaussian is a model. And then if I speak to engineers, they might talk about a complete system. So what exactly do we want to describe in terms of models? I thought the way I could get that across is to talk about a task that we played around with our robots that's inspired by what people might try to do. So imagine a situation like this. You have possibly a number of different types of liquids that are filled into those funnels. And we're asking the question, if the finger was taken out and the liquid were allowed to fall into the cup, will it splash? Okay, so it's a straightforward question. It's the kind of question that is so intuitive that you could imagine asking small children and they would give you perfectly sensible answers. And so here's what would happen. It depends on the size of the cup. It splashes a little bit if the cup is too small. If you have a giant container, then it doesn't splash. Right? We all know this, and this would have been your intuition. Now, if I tell you that I have a different kind of liquid, maybe the viscosity has changed, is it going to splash? Okay. In your head, you have some kind of reasoning that says, well, it depends on what the viscosity is. And so what you might do, especially if you're allowed to kind of think about it a little bit, is either simulate or perform some kind of an experiment like this that says, the last time I played with this liquid, if it behaved like that and if it was thick and sticky, then most likely it won't splash. If it was loose and free to flow, then it would splash. Right? And so this is what happens. Because such a thick liquid doesn't splash, it actually cleanly stays inside. Okay? This is the kind of reasoning you have to do if you want to do planning for the things I'm talking about. Okay? So how does this reasoning actually happen? So the claim here is actually that you have to have some models. At the very least, you have to have some level of intuition and common sense models. This is a claim that has been advanced very effectively by groups such as by Josh Tenenbaum at MIT. In fact, those examples are inspired by things I've seen him say. And I'm not really going into exactly what is inside the brain of the human. I'm more asking what would be effective ways for engineers to acknowledge this and somehow do things. So in this particular experiment, what we did was to say, okay, so we're going to build up some kinds of models. So in our case, the model was in the form of a simulator, and the simulator had certain parameters about this task that had been given, such as the shape of the object, descriptions of the fluid. And then what we wanted to do was to calibrate that simulator to reality, and then having calibrated that, use that in a planning process. Okay? Because this is not the core focus of my talk, I won't take you to the details of this method. I just want to give you a glimpse for what I want to capture in a model. So the first thing you notice is that when you're thinking about what the simulator should encompass and what you want to represent about it, you realize that the properties you want to get right depend on what the task is. If you want to worry about whether it's going to splash or not, it depends a lot on viscosity. If you wanted to represent something about its visual appearance, maybe it depends on something completely different, like surface tension. Right? You also realize that different tasks have possibly kind of things in common, such as my observation that you can first stir and find out and then use it for pouring. And that's exactly what we did in our experiment, is that we were looking at ways in which you could do parameter estimation with one task and then transfer to another task. So this is now a fundamentally deep kind of transfer, and that I don't just mean when you change the viscosity of this, still stir in a certain way. I mean, use this to figure out something underpinning, which then informs how you do a completely different task. To an engineer, this kind of a diagram would just seem obvious. Yes, this is what you do. I think most humans behave like this, and cognitive scientists would agree. But somehow in the robot learning community, especially when we think about machine learning, there's a lot of controversy about what you want about this. So the claim I'm stating up front is that, to me, the utility of having good models that somehow capture the structure in a deep way is the possibility that it allows this level of generalization and reasoning. And that's why we would like to have them, right? And then we're trying to ask how we want to marry that with other things. So for instance, the way in which we actually did this is that we took actual data from how people were stirring liquids. We looked at the realized behavior in a number of different simulators, and then we perform a Bayesian optimization loop to figure out what the best parameters are. There's one example of how you might reason about a model. And then that allows us to optimize pouring policies.
Good question.
Yeah.
That theta f
Yeah.
now limits the kind of transfer that you can also do.
Absolutely. Yeah.
So
Yeah.
that's-
Yeah. And so this is exactly the point, is that just like historically in engineering, you would have had 10 years of debate about what are good parameters. I think that the point I'm saying is there's no getting away from some of that thinking. You have to do that thinking. The question is, can you find theta f's that are coarse enough that you say just enough of what you want to say and then let the model do the rest of it? So it's in that balance. So here what we are showing, and this is all the left side of each of these is something in our lab, is the robot having figured out these kinds of properties, how it figures out how to pour in the most effective way with the least amount of splashing, with this being its internal representation. Right? So that's what, yeah, go on.
Give a bit more details about that internal simulator. Like, I'm trying to get a sense for what was the parameter space, how was that simulator?
So it really is just an NVIDIA Flex simulator with a kind of particle-based approximation to the fluid, and in that interface we are given high-level parameters that correspond to all the fluid dynamics parameters. So viscosity is an example, and so what we were really playing with there was viscosity.
So how high dimensional was that Bayesian optimization landscape?
It wasn't very, because we were only searching over that low dimensional space of parameters. It could get high dimensional if you want to explore with a lot. And actually, when I get to my main result, which is what I'm talking about next, I'll tell you a little bit about this dimensionality question. So that whole preamble was to give you a flavor for, kind of shake you up a little bit and say, think about models in this way, right? So models are not just things that are hyperparameters in a network, but there actually is more to it from the physical point of view. Now I want to take you a little bit more into kind of robotics specific things. So in the robotics community, we've been talking about these kinds of representational issues for a very, very long time. So in fact, my PhD thesis work was on learning to walk, before we had things like Atlas. And so it was still a worthy question for a single solitary PhD person to ask. And so I was looking at things like learning to walk, and there's been some very, very elegant work that's been done by people like Dan Kodacek and collaborators, who showed that a good way to construct controllers and a good way to describe biological behaviors of the same control phenomenon is to think in terms of a hybrid control representation, something like this, where what this is depicting to you is the movement from an initial state space to a final set of states over time. So time flows from top to bottom. And so if I initialize the system anywhere in a large state space and I run the controller for some amount of time, then the controller ends up in a small set of states. That's what controllers do, right? And then that small set of states sets me up in the next one and next one. And so you can think about a large task compositionally in terms of a smaller set of this, where the representational question, the equivalent of picking the theta f, becomes what funnel, what shape, what switching logic, and so on and so forth. This constrains you, but it constrains you in just about the same way as picking a basis function in function approximation, in that, yes, you're making a choice, but then the choice allows you to do quite a bit, right? And so what we are trying to ask is, to the extent that when people have handcrafted controllers, and in fact, today, if you look at Atlas doing its backflip, it still is doing that. It's the same first author in the same company. And so when you have these kinds of representations that are working well for people, can we somehow use that inside a learning model, and would that give us any real leverage, right? And so we are interested in having flexibility in the sense of being able to answer questions like this, which I would claim would be hard for us to answer unless we had some kind of structure. So if you want to ask a question like, so in this case, the task for the robot is to kind of go from one object to the next in a sequence, and if it hits a certain kind of object, it should flip around. So it goes A, B, C, D, E, and if it hits E, it should go back around, and then it just does this in an infinite loop. It's a kind of trivial program you could write, okay? And if I wanted to ask a question like, what would happen if I moved my objects around? What would happen if I insert a new object? What would happen if I wanted to ask, will this ever terminate? Things that a regular engineer would just ask naturally, right? There's simply no way to answer such questions if you leave everything implicit. So you have to somehow elicit the structure so that you can reason about it a little bit. And what we are arguing is that if you're sensible about your choice of controller structure, there are ways of marrying this. So with respect to that particular inspection task that we kind of cooked up, it's a tabletop inspection task with a collection of objects. What we want to see is it possible for us to go from a human demonstrating this task, not actually telling us what the task is, just demonstrating it, and is it possible for us to do system identification of this full structure, including the low-level controller and the high-level switching logic? Okay, so here's how we go about it. So we actually exploit the neural network models where they are strong, which is to make local predictions about, in that whole sequence, I have 1,700 or so frames in a typical demonstration. If I gave you the input image, could you tell me what would happen next? I just want to make local predictions, right, from pairs of images and next velocities. This network is not powerful enough to represent that whole program that I showed you because it doesn't have memory, it can't represent the logic. But it's good enough actually to make sort of decent local predictions. We use those local predictions to figure out what matters in the image, because nobody told us that there are objects in the image and where they are and all of these things. They were all left latent, right? We just have as a structural description that everything we want to describe can be thought of as some sequencing of local funnels, where the funnel is essentially just a proportional controller to a control theorist, or a particular kind of parameterization of a function to a statistician, right? So we are saying our underlying task model is a collection of these switched together. And I don't know with respect to what and to where. And so we can pick that up by doing sensitivity analysis on a collection of this, and then representing it in a sequential Monte Carlo fashion and trying to figure out what must be going on underneath. Right? So I found out that these are all salient places by looking at the sensitivity of this network. And then that gives me a collection of hypotheses for if my robot is moving like this, is it moving here, is it moving here, is it moving there? And each blue line represents one parameterization of something like this. So that's my task model, okay? So I've put in structure in the sense that I've told it that this is a useful basis. And beyond that, I'm letting the kind of model learn for itself. Right? And so this is what it looks like. So here's a typical video of the demonstration. And what this is telling you is the number of controllers that are being picked up. You shouldn't really worry about this. What this is telling you is that by looking at diversity of the controllers, if the predictions are sometimes here and sometimes here, then I know that that's a time to introduce switching. If all predictions line up, then actually I don't need to introduce switching, right? So from clustering those things, I actually get that in the underlying world, there are that many objects, and those objects are located here, which I picked that up from that input, which I can reason about symbolically by saying now there's only 5 objects in the world. So I'm looking at what is the sequence in which you visited those objects, which can be interpreted using your favorite string parsing or grammar learning kind of approach to say that that's what the underlying task was. So we've gone from essentially just a video input of this as the person is demonstrating to a description that says your task is to execute this sequence, where each sequence refers to one of those controllers in my previous slide. Each sequence is a reach. The one bit that I should say in all of this is that the original controllers learned in terms of joint angles. So we train one more network that then grounds those joint angles into world coordinates, so that then this program that you've learned can actually be generalized to different orientations of objects. So here's a learning loop in which we have put in structure, and our structure was specifically that this way of thinking in terms of sequencing of funnels is a useful description of control tasks. But then we've been able to be fairly general in all other ways so that we can actually learn a switching control strategy from demonstration. Right? And then we tried to extend this to a slightly more interesting task to us, which was to find ways in which you can pick up objects from a table and stack them up. So here are kind of snippets of examples of the vocabulary that we use to generate the demonstration.
Before this, in the previous slide,
Yeah.
did you run into credit assignment kind of issues, as in if I'm learning this model that's first trying to just predict based on the visual scene what's the action being taken, is the model bogus, or is it the case that I've learned good models and I can trust its predictions, and the fact that it's getting confused and predicting two different things gives me an indication that I should be switching?
So I would say that it comes down a little bit to the same kind of thing as how you would think about a mixture model. So I'll come back to this question. So the short answer is, at this point in time, we are asking for a best description in terms of this vocabulary, right? And then what you're asking is, could there be two best descriptions and you pick the slightly less interesting one? It could happen. And then you would deal with it in the same way that you would deal with every other function fitting kind of paradigm. But I'll come back to it because I'll describe one more variation on this theme.
I mean, what would it take to extend this to hierarchical programs? So right now, it's clustering. So you can write programs which are more like regular expressions.
Yeah.
But if you have infinite depth with compositions that are hierarchical,
You have to find some way to chunk it. So let me go through one more section and then we'll discuss this point. Yeah. Yeah, so actually leading up towards that, so the next task we looked at was hierarchical in the sense in that we wrote the program of how to demonstrate it using a vocabulary that looked like this. So we demonstrated to the robot that the way in which you stack is you first go above the tower, you lower the gripper, you close it, blah, 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 right? So this is what we told it, and this was our internal hierarchy. And so we went through the exact same process that I'm telling you. So you start out with demonstrations, do the sensitivity, and then you ground them, and so on and so forth. And here's what the robot learned to do. So this was our input kind of program, and what you see there is a video and a depiction of the output that it has learned in its own internal representation. And really, what it does is it learns it in terms of these sequences. So it learns to put the sequences together. The bit that actually goes back to, I think, Sai's question, is that actually the robot is not smart enough to figure out that this sequence is the same as this sequence. You still have to do some program simplification and things like that afterwards, right? So it says this is one thing, this is one thing, that's one thing. But it does learn that this is how you can sequence them. And what's interesting here is that to a robotics person, already this is a pretty sophisticated level of identification, because all the other things we knew how to do before this was just learning parameters in a single controller. So now we are actually beginning to approach system identification in a genuinely hierarchical sense. And of course, I mean, there are lots of questions you can ask. So exactly this kind of generalization question of what have you given up because you said this is your parameterization. The most interesting one that only occurred to us after we finished the whole project, I mean, we knew about it, but we didn't consciously think, was that we were specifying that every local task was a reach task. Whereas you could have an avoid task as well. I want to reach here, but I want to avoid here. And we weren't representing that. So there was no clean way in which you could take, a reach controller and represent a void. So those kind of decisions do matter, right? And so this is a trade-off when you're trying to do model-based work. But then what I'm trying to say is that to the extent that that is how the engineering design process has always worked, we're trying to see how we can marry these two things together. So the next thing we did was to begin to take on some of the questions you're asking, which is to say, can you keep this level of structuring? So can you keep this idea that you're going to have switching between controllers and so on? But then can you make the whole thing look exactly like how a typical neural network model would look? And so what we wanted to move towards was to say that there's a lot of excitement about using things like mixture density networks within a neural network context. Can you somehow put that funnel kind of representation at the end of this and describe one network that does this? So the network's job is, here's your input, just tell me what the action should be. So just learn the whole controller and then learn the fact that it's a switching model, right? So our starting point is the well-understood idea of a mixture density network, whose role was to say that I want to describe a complex probability distribution in terms of simpler components, and then I want to learn the weights for them. Now, in the way that mixture density networks were originally introduced, the objective was to solve the statistics problem of approximating a complex thing with a simple thing. There was no requirement whatsoever that the simple components map to anything else. In fact, they did it because they were just carefully chosen simple components. So what we want to do is to somehow map them into an architecture like ours. So we introduced this variation on the theme, which still looks like the previous one. And the bits that we've introduced is actually this bit. So what we did is to create a different form of a switching network. So it's still a density network that builds from components, except that we are restricting it to switch using a bottleneck layer, which is a finite set of categories, finite number of categories. And then what it's going to output are the mean and variance of the goals, just like what I had before. So the goals were the points where the blue lines were ending up, right? And so, for those of you who played with these kinds of models before, the introduction of a Gumbel softmax, what it does is, as you change the temperature, it approximates, a single category. But in the beginning, it actually keeps a diversity of categories. And what we want to do is to take the controller parameterization that is loved by control theorists, and 95% of the world's controllers look exactly like this. Except what we've done is to take this structure, put it into here, and then find a way in which we can just learn the bits that we want inside this architecture using the network, right? And when I say take this structure, what I'm saying is that this is a high-level description of the task. You still have to do it from pixels, which is what we are doing. So we're still doing all of this to go from pixels. But then we're saying that the control bit, the bit that really matters for describing the task at that level, is not that complicated, okay? And so you can kind of encode this in the network. And here's what we find. If you just did, for the data that we are interested in, which is the tabletop manipulation task, which is a sequence of visiting these objects, if you just fit a mixture density, then what you get is something like that. It does an averaging so that it just tells you that you're typically going to do one thing. Whereas what we get from our network is a clean switching sequence, which corresponds to the switching sequence of you visiting different objects, right, over time. So this is all learning from the data. So we're going from data which doesn't tell you what that structure is to a model that tells us that this is the structure. And we've applied this to a few other kind of problems. So here's another problem that is very well liked by control theory people and reinforcement learning people, which is to swing up and balance a pendulum. The interesting thing about this problem is that if you were first taught as a control theorist, as I was, then you will realize that this is elegantly simple and beautiful, which is that there's only really three things that happen here, and those three things can be described in terms of linear functions. And if you do it like that, every controller you learn will always look like that. And it turns out that those three things are discovered by our switching network. It discovers that there's a swing up phase, there's a balance phase, and so on. And likewise, we did another task which had to do with you switching phase when you open a box, and then it learns that you first have to reach and then you have to do something else, right? So what do we really get from all of this? So there's an interesting observation. So we did all of this from the point of view that we are very much interested in interpretability, structured models, because those structured models lend to us the possibility of doing additional forms of reasoning. Okay? And that's what we set out with. But of course, you have to ask yourself the natural question, was all this necessary? Would the underlying model have done it anyway? Would some other model have done it? The answer is that if you have a straightforward controller task, and by straightforward I mean that there is no switching logic, there's only one state, then our model doesn't do much better than anything else you could have done, which is also equally sophisticated. And subject to noise, we might even be slightly worse because of our training procedure. But when there is switching logic that is intrinsic to the task, then we do substantially better, right? And so this makes sense because that's when most methods for training that I'm aware of actually struggle, is when there is a deeper underlying logic that isn't being picked up by the network, right? So for us, the takeaway here is that the need for all of this structure is the fact that the world is structured like that. And we are just trying to find a way in which we can somehow bring that into our kind of training procedures. So that's kind of one direction on all of this. And if you kind of mentally remember my arrows, this is the direction of us going from human demonstration to some kind of a slightly more abstracted description. Then we were curious about, can you also do a little bit more of the other side, which is, if you know that you have this kind of structure, can you somehow bias policy learning or learning to act by using that kind of structure? So this is work that we did, which was motivated by this idea that, so if you're familiar with reinforcement learning, there's a very straightforward way of thinking about lots of different control tasks, which is called the policy gradient method, which in simple terms is the intuition that most of the time you can define a policy that takes you from state space to action space, and that might be much lower dimensional than even your state space. And so what you're interested in is to represent that in a certain way and then do gradient descent to try to find that policy. Okay. So one very simple approach to using it, and this is by no means the most sophisticated way to doing policy gradients, is called reinforce, which is that you simply take the cost function that's defined in terms of your long-term reward, and then you take the gradient of that, and then you add something called a baseline, which stabilizes the variance of this estimator. What we did was to say that you can take that same loop that we're all familiar with and we've come to love, and you can change the policy to have a factored form. Okay? And the factored form is essentially telling you that what I had as switching logic or program goes in here, and what I had as the interpretation from pixels to some intermediate symbol set goes here. This bit I represent as a network, this bit I represent as just a program. Okay? So in my previous one, the program would have been the bit that I learned that says you go from A to B to C and so on. And what we are saying is that in a lot of tasks, we actually have a pretty good understanding of what that program is, right? And not only do we have understanding, we might actually have very good technical analysis of convergence properties and stability properties and robustness properties of that side. And we are asking, is there a way to marry the two? The short answer is yes, there is a way to marry the two. And in fact, if you do it like this, and if you set it up in a certain way, you can preserve exactly the same training procedure that Reinforce used to use. And then what it turns into is just training this network to produce the right symbols which have the characteristics such that this controller is actually useful. Right? So I've just defined reach, and I haven't said reach to where and reach with respect to what. But if the network could learn those things, then actually reach is enough. Right? And I can actually do quite a bit. And that's the intuition here. So there's a kind of small technical result that actually says that it goes through. We haven't changed anything about convergence properties of policy gradients by factorizing it in this way. And the training procedure essentially just becomes the process of us defining a loss function where we just took that reinforce, the gradient description, and we turned that into a loss function. And so we trained the baseline, and then we trained the reinforce loss. Okay.
Quick question.
Yeah.
What's about reinforce that allows you to do it?
It's just the most general form. It's actually not the most sophisticated one, in the sense that you can have much more sophisticated gradient estimators with kind of stochastic, mini batch, and so on and so forth.
Can you extend it to any other policy gradient methods?
In principle, we could have done it with any other. Yeah. In fact, if we did it again, we might try it with a more sophisticated version. Yeah. But the bit about what we are saying is more in the fact that you can factorize the policy like that. Okay. So here are some examples of what we've managed to do with that. So here's the pendulum swing up task. The task is defined in terms of go from pixel description. So we don't have a state space description. So we're just giving you the images. But what we are saying is we know that this is the way to stabilize the pendulum. We don't know what the pixels map to exactly, but we know that that's how you do it. Right? And in many domains, this is how it works. So specialists can tell you that this must be the general structure. What they get wrong is the embedding. And so what our procedure allows us to do then is to train in the loop. And when we train in the loop, we actually get improvements in terms of the convergence rate. So if we did it without all of this structure, it takes much longer to reach the same level of performance than if you did have this kind of structure. And what's going on in all of this is that we are really regularizing the latent space that's being learned, right? So when I'm just giving you the pixels, somewhere you have to discover the fact that there is a joint angle and there is a state and so on and so forth. That's being picked up in this process. But by telling you that it must fit this program and the program must be useful in the task, I've actually regularized the problem quite a bit, and I'm forcing you to pick up that, because with any other variable that you pick up from the pendulum, like if I picked up, reflectiveness, it would be useless when put into an LQR controller, right? So I'm forcing you by the task to do something like that. So we did this on a sequence of other tasks as well, just to see the extent to which it could be useful in planning. We did it with Minecraft, and of course, as you all know, this is essentially just an A-star style planning problem of getting the agent from one place to the other in one of its instantiations. For us, the important bit was that we deliberately just picked a library off the web for doing planning. So this was literally a code library that we didn't touch in any other way. We plugged it in, and we said we know that much. And then the network has to figure out what inputs to feed to that library from the pixels using our training procedure with perceptor gradients. Okay, and it does that. It learns to perform the task. And it actually does it with a significant boost. Now, the x-axis has actually changed from my previous slide. So the difference between this and this is actually much more substantial. So we actually do begin to get more and more of a boost the more and more complex the task is, exactly like in my previous example. So then, we can find out that the latent space has some meaning. So when we look at confusion matrices, our description and the discovered description lines up pretty well. And we can begin to stack them. So just like I can do it for one, I can stack them, and then along the way I can try to do a closed loop with an encoder and a decoder, so that I can make use of those kinds of representations. And by the time I'm looking at stacking multiple tasks and so on, the learning curves begin to look substantially different. We're beginning to get substantial kind of improvements in learnability. And the most exciting bit of all of this result is that the symbolic descriptions that we are learning along the way in the bottleneck layers actually are useful. They tell us something about the task. So it's discovered that actually the underlying task in all of this is just a grid world task. It's not obvious if you look at it from pixels, but the underlying task is a grid world task, and that's been discovered in this process. And so we can kind of describe the task now in terms of relational labels instead of just the underlying state space. So we've kind of gone up and down the loop now. So first I showed you some results that tell you a little bit about, if I've given you demonstrations, then how do you go from demonstrations to useful abstracted descriptions that kind of are compatible with engineering ways of thinking. And then we looked at, if you had some description from the engineers, how would you put that back in? Okay? In both of these, we are doing more and more. So I want to end in maybe the next 5 minutes or so before I come to my concluding remarks, by giving you a glimpse of some work we've been doing about more explicitly playing with the latent space. Okay? This is the bit where I said I have more slides than I want to cover. So I'll go through it quickly by picking on the highlights, but I'm very happy to discuss all of the details with you if you have specific questions. So the thing we were interested in when we started doing this work was still thinking about the learning from demonstration framework of people giving us instructions. We wanted to ask, how high level can the instructions get? So if we really want experts to give us information, like your typical car mechanic or your typical brain surgeon, actually they both speak in very similar ways from the point of view of the machine learning model, then they're going to give you very high level information such as, when this is a bit soft, then insert it like this. And you have to ground everything else about this. You have to figure out all of the rest of it, right? And so we were interested in this question of, how do you go from high-level descriptions that are matched with otherwise unlabeled data and go through a labeling process so that you figure out that, oh, soft meant this, okay? And so in our first experiment, we were playing around with things like color and size of objects and shapes of objects. And so what we did was we took what is by now a fairly well understood and well used architecture, which are autoencoder models, and in particular disentangled versions of autoencoder models such as beta VAEs. And then what we did was to force these models to perform a classification task as the end result. And what we want from all of this is that I'm giving you a collection of descriptions of objects. So what you see in this matrix is just like kind of sprites with different colors and shapes. And what I want to force you to do is to organize them in such a way that if I forced you to classify using one axis, then you do a sensible classification. The only way to do that is to then get size this way and shape this way and so on and so forth, is to make the basis vectors be meaningful, right? So the way that we construct a model looks something like this. So this bit, it's a fairly classical kind of description of how a beta VAE type model would work. And what we've done is to essentially add the classification term at the end of all of this, right? So we're saying that you still have to look at the KL divergence, you still have to reconstruct, except I also want you to do a good job of classifying using your basis vectors. And if you do that, then what you end up with are classifications that pick up the labels we really care about, which is size descriptors, color descriptions, and so on and so forth. And then, so we did that, and what we found is that if you do it the way we've done it, then you actually get pretty good classification performance, and that actually gives us human interpretable output. But then we went on from that, and in our current work, what we are looking at is to try to use these representations inside the action loop. So we want to learn disentangled relational representations, where the relations correspond to things like, is an object on top of another object? Is the object in between something else? These are all labels that we want to learn, and we want to learn them as axes in this latent space, so that we can then map that onto planning later on. Okay. So without describing the model to you in the interest of time, I'll just show you the videos of what we are able to achieve from this. And I'm happy to talk about the model with you if you're interested in it. So here's what it lets us achieve. So it lets us cluster things in terms of, when the description has something to do with moving an object from one region into another region, when the object has something to do with putting one thing on top of another thing. So these are all for us basis vectors of descriptions of a concept, so that when the person says put it on top of, it's invariant with respect to what the object is, it's invariant with respect to the position, but you've discovered that there is this notion of on. And so we've learned a number of these things, such as jump over something, go in a C shape, go from one thing to the other, and all of that is now allowing us to do things like this. So we can take an instruction such as put a cube on a cylinder, or make two cups face each other, and then the robot actually performs those tasks when we are done with it, right?
So I have just one clarification question. In the previous slide, those were just like exploration of one latent variable.
That's right. Yeah. And so the objective there is to use the model in a closed loop like this. So I want to end then by bringing all of this together and kind of reminding you that for me, as a roboticist, when I look at all of these problems, what we have to do is to solve a collection of interrelated problems where each thing drives the requirements of another thing, right? So we want to do learning from data in its very classical sense, except the data is relatively limited, and the thing we want to learn typically is to extract what look like specifications. We want those specifications to map to representations that other people in the domain have already thought about before and can do reasoning about. Then we want to find ways in which we can somehow enforce that in the policy learning kind of loop. So I wanted to end then by showing you an example of some current work that we are trying to do. So in this video, you see that fruit cutting task again. And so this is what the person is showing the robot. And if you just naively kind of copy what the person has shown this robot, you find that actually it does pretty badly. Which is good for a machine learning person because it says there is some need for learning here. And so these are kind of just naive open loop learning. So if you just said, okay, I'm going to learn how to do this, then you find that it's actually pretty hard. So the way we solve this problem, it's quite interesting from a cognitive perspective. So because we have no other perception of where the fruit is and where the peel is, the way we solve the problem is that the cost function that the robot has is to classify sort of whether the trajectory is going to get stuck in the peel, okay? And that classifier, by the time it gets good at predicting whether it's going to get stuck in the peel and get a bad reward, will end up giving you implicitly the shape of the peel, right? And so then if you give that as the kind of parameterization of what this robot has, it figures out pretty well how to exactly scoop only that bit, and it figures out all the other stuff about how to control the forces and so on and so forth. So this is a typical task that we are going after. It's fairly challenging from a robotics point of view because the object is quite high dimensional. The underlying physics are quite interesting in that it's not immediately obvious what to parameterize and what not to parameterize. So we're playing with all aspects of what simulator to use, what descriptions to use, and so on and so forth. But also what specifications to use. So as I said, we are only playing around with fruits because we haven't gotten around to phantoms of brains, which is what we really want to do. So our end goal with this project is to work with actual surgeons who are doing tumor removal and to do exactly this process. And the objective function there is to try to take only the tumor and not the rest of the healthy tissue, which if it's in your brain, then even 1 millimeter matters. And safety specifications are important, so don't go near a certain kind of artery is literally a life and death matter. And so one day when we reach something like that, which might be 10 years away, all of these problems are going to play a role in that. And so we are kind of taking baby steps towards that and trying to see how we can line up all of our robotics technology towards it. So I wanted to end with a few concluding remarks, which is that having worked in this area for quite a while and having looked at lots of different problems ranging from locomotion to today manipulation, we believe that representations like hybrid control systems are fairly powerful with respect to describing what you want in the task. So the hybrid control representation is a marrying together of low-level controllers with higher-level switching or programmatic structure. Right? And so if you look at it, then all the results I've presented to you in one way or the other kind of marry these things together in different ways. And so what we're looking at is ways in which we can define models that can do a good combination of these, and then asking the question, what are judicious choices around them? The reason we want models like this is because we want to do a number of other things that from the application domain point of view are absolutely essential. You want to be able to reason about causality. You want to be able to do coverage-based verification. You want to be able to ask about long-term behavioral properties such as, will this controller do this, or how often will it do this? Right? So there's no way you're going to deploy serious applications without answering these questions. Having representations like this allows you to answer such questions. And so what we are trying to do is to come up with tools that gets us there while still doing everything else that we love about data-driven ways of thinking about model learning. So with that, I'll stop. I'm happy to take questions now and also to chat to you during the rest of my visit.
Great. Thank you. So we have a few minutes for questions. So, I mean, I would like to pick your brain in terms of like, what do you think is the right visual representation for generalization for all these tasks? Because like inherently all of these are sort of 3D, and also I think like the approach orientation matters because you want to grasp something, right? So it's just stuff post. But like I think at least in the first 2-3 works, it was 2D coordinates, and also like with a fixed camera view. So I'm not sure how well that would generalize.
No, that's absolutely true. We do them with fixed coordinates simply because our focus of attention has been on other things. We could quite easily get our robot to move around. In fact, the robot we use, PR2, does move around. So we could easily make that be a multiple coordinate view kind of problem. But you're exactly right. So in almost all the problems we are working with, it has to be a 3-dimensional representation. And it has to be a representation that can somehow be correlated with the rest of what you know about physics. So if you have a 3D representation, you can reason about physical laws in the way that you're comfortable with. So there's no getting away from that. The bit that's really thorny for us at the moment is that vision is probably the best understood and best researched modality, but everything else we want is not in that channel. So all of the haptic information is kind of missing from vision, and the correlation is very weak. So that's something that we're thinking quite a bit about, and we're looking at new sensors and so on. And then that brings us to the question that there might be many, many properties you want to learn about objects. If you had mass asymmetry in a ball, it can only really be picked up from a dynamic exploration. So this business of going from single frame labels to exploring and having a mental representation that's almost a full simulator is where the kind of big challenge is in my thinking.
Yeah, I guess you care about things like stiffness and all that as well. You need like force sensors. So I guess my other question was for physics. What have you learned from say playing with all these different physics engines? I guess because none of them I guess would really represent reality. So at the end, some people are trying to learn residual physics or just like if you have some intuition and you pick like the top n parameters which matter for your problem, like I don't know viscosity or something else, and then do MLE map on that.
Yeah.
So.
So at this point in time, I would say that if you have not too much physical contact interaction, simulators are better. If you have a lot of that, simulators are not good. We are in desperate need of much better simulations of that side. And simulators seem to be tuned to the tasks that they were originally invented to solve. So, MuJoCo came about from the DRC experience of Todorov. They're extremely good if you're modeling locomotion robots, not so good if you're modeling other things. And then other people today are trying to build kind of manipulation simulators, and they're still struggling with kind of, am I solving grasping? Am I solving general object properties? So there's still, it seems to me like we're still in early days, and there's much more to be done.
So, one comment that struck me was, you say how evolved the vision is. So, for instance, the work that you're doing, where you have a perceptor and you have a policy. I mean, given this, era of pre-training models, it makes more sense that we fix the perceptor, but do learning on the other side of things.
We could do that as well. It's a very good observation. At the time when we did that work, we were more trying to explore how you would put in specifications. So the question came from there.
Yeah.
But you're right. I mean, in this era of pre-trained models and so on, if you could have, very good object detector networks trained over millions of objects all over the world, it would make a lot of sense for that to become standardized and to use it. So in fact, the immediate next thing we were toying with doing with Perceptor, which we haven't done, is to then factorize the policy even more and say there's a vision component, there's a kind of learnt component, and then there's a structural fixed component. And that would look more like what you're saying. So the vision component would be a pre-trained network. There'd be a small level of post-training on the job, and then there would be kind of fixed structural insights. That would make perfect sense.
Yeah. Also, I'm just wondering how much it makes sense to train a perception in a reinforcement learning loop. Because perception, sure, there are task-specific things, but if you can put some human intuition or knowledge into it, you might be able to just do it using supervised learning, and then, just a little bit of fine-tuning.
Possible, yeah, it's possible, yeah. So in our experience, it's not so much that you're learning perception from scratch, although, we did that there because we wanted to show something. But going forward, for me, the more interesting thing is you have to leave a little bit of leeway to decide which bit of the perceptual channel matters to your description. That has to be left for the later bit. But how that channel is processed could well be kind of pre-trained. Yeah.
Great. Well, there's no other question. I have one more question.
Yeah.
So, the work where you're learning these base level controllers and a sequence of those base level controllers. So a simple task, for instance, if the task is to draw a square, and if I only have demonstrations going one way, right? So basically, you are now biasing your learned controller to just do the task, right? There's no way it's going to find out that you can do square like these, or go the other way, or draw.
I see what you're asking.
And I'm just wondering, like those kinds of things that comes very naturally to us. It's not really about the how, I guess, how the movements are done, but it's the context, the complete context.
Yeah. So I think the argument I was making, it's in two steps. One is that the learning of the original square is where you do a lot of detailed sensory motor stuff. The later reasoning doesn't need that anymore. If you've somehow learned all of that, you can reason at this higher level. So if I've learned lots of these, exactly like in my tower building example, where it has learned that there are these four, the observation that those four are the same is a program simplification step that can actually be done completely in the abstract. So our first answer would be that then bring in the rest of computer science and do that. And the second answer would be that maybe then that is a target of a second level of learning problems. But then that learning problem doesn't need to be done from scratch at the low level, and you can kind of separate these two things.
I mean, that's what like recursions and program languages, they try to do that. Right?
Yeah.
So,
Yeah.
great. Well, thank you again. Thank you.
Yeah, you're welcome.